Okay, well, let's get started. Today, we're very pleased to have Dan Koditschek from University of Pennsylvania talking to us about working compositions for correct execution of robot task specifications. So take it away, Dan. Thanks.
Great. Thanks so much, David. Thanks. It's a great pleasure, a very kind invitation. I'm really eager to try to engage with this community. I think you'll see that we could use help from your community, and maybe we'll get some of you interested in some of the work. Yeah. Okay. So I want to just start out with a general sense of what I'm all about in my work in my lab. And, roughly speaking, there's a bibliography at the end of this slideshow, and there's a list of references in the abstract for anybody who wants to, track some of the papers. Roughly speaking, if you're in the business of the sciences of the artificial, as Simon said, that you concern yourself with building architectures to achieve tasks in environments. And in the world of robotics, we've got this environment, which is the Lagrangian world, according to Newton and Newton's successors. We're building architectures in green, and we're operating into environments. We're typically imparting forces and torques and pushing energy into environments, and then we're listening back to what the motions are. Sometimes we get energetic information back. Right. And so it's our job to close this loop. We have wonderful sensing algorithms, signal processing algorithms, coding. We've got a growing arsenal of actuation technologies. There's an explosion of material science capabilities. And, so when you close the loop around the environment, you end up with a Newtonian dynamical system, sure, but it's going to have some artificial terms in it. It won't be entirely Newtonian. The Newtonian point of view was generalized by the 19th century physicists in terms of energy relationships. And it felt up enough to show that even if you don't have perfectly Newtonian components, if you have a reasonable dynamical system and there's any stability at all, you're going to have an energy-like quantity, Lyapunov functions. What we do then is we try to prescribe and then execute the work that we want our robots to do on the environment in terms of designer attractor basins. The idea about passing from the signal spaces, the sensory motor flows of the physical world into these symbolic relationships, of course, goes back to at least Poincaré and the development of topology and eventually algebraic topology. From our point of view, the golden spike in making this be potentially formal was Conley's understanding that you can decompose any reasonable dynamical system into a cover by attractor basins. So if you take that point of view, then your job as a roboticist is to accept from the boss's so here's a state space, and let's say these degrees of freedom are all the environment degrees of freedom, and these degrees of freedom are all the robot degrees of freedom. So you're closing the loop. So your dynamical system is on this plane, and the boss tells you what the goal is. The boss tells you that there are certain states of the robot world conjoined that you need to avoid. There, you don't want to fall down the stairs, or you don't want to break something. And it's your job to then build an architecture with an intermediating logic or intermediating set of algorithms between the sensors and the actuators that has the effect of producing a vector field such that the vector field engenders an energy landscape favorable to the boss's goals, namely since there's always dissipation, namely you want to make sure that the end state, the goal state, is low, it's minima on these energy landscapes, and that the things that you don't want to have happen are high in these energy landscapes. One of the several virtues of this point of view is that you automatically get an abstraction. This is a kind of abstraction of agency because, as you all well know, if you change coordinates, if you deform the model geometry into a topologically equivalent, but a metrically more exact replica of what's going on in the particular environment, then your model solution, your model vector field deforms into a solution to the particular case. So that's one kind of abstraction that I'll be talking about. The wrinkle in robotics is that we don't have classical dynamical systems. Unfortunately, we don't have them because we're stuck with what are called hybrid dynamical systems. Hybrid dynamical systems because you've got a legged machine and sometimes you have one leg on the ground, sometimes you have two legs on the ground, sometimes you have no legs on the ground, or equally interestingly, you have under-actuated degrees of freedom. You never have as many actuators as you would like. You don't have the power density that you would want, and so there's been an understanding since the 80s started by Roger Brockett that if you have a degree of under-actuation in your ability to affect the environment, then you're stuck with discontinuous controls. You can stabilize with hybrid controls, but you can't stabilize with smooth controls. Now, fortunately for us, work that's been done by a former postdoc, Matt Kallheim, he's now a lecturer at Michigan, together with Paul Gustafsson, about whom I'll talk soon, later in the talk. Matt was able to show that a reasonable model of hybrid dynamical systems also admits Conley's fundamental theorem. So you also inherit the decomposition of any reasonable hybrid dynamical system into attractor basins. And I'll talk a little bit more about what I mean by reasonable toward the end of the lecture. Okay, so that's good. Thus, what I get to do in this talk is mainly discuss the kinds of compositions that we know how to build up in physically grounded machines that have, on the one hand, provable properties, on the other hand, they are empirically practicable. All right. And so then at the end of the talk, I'll be spending my time trying to convince you that, yeah, I guess category theory is really, really important. But from my narrower view, category theory implies a type theory. You don't have a category without a type theory. You don't have a type theory without a category. If you have a category theoretic model of your system, then you have a prayer of developing a practicable type theory. And that promises some kind of a formal programming language, wherein the software doesn't take its hardware model in Turing machines. It takes its hardware model in these hybrid Lagrangian dynamical systems. Okay, so that's, roughly speaking, that's who I am, and that's what I've been trying to do for about 30 years, me and my students. And now I'm ready to present an outline of the talk, unless there are questions about this, very, very general overview that I've tried to give you, so you have some sense of who I am. Right. All right. So I'm going to spend most of my time on this bottom-up piece, where I talk about letters that denote basins, and then we try to compose those letters into syllables, and the syllables are, roughly speaking, parallel compositions of basins. And if you string those syllables together, you begin to get words of ascent when they're energy barriers. And I'll try to be very specific about this. So we'll talk about attractor basin compositions. We're interested in abstracting the environment. We're interested in abstracting agents so that we can compose them. And what we end up with is this joint level, body-centric reactive planning environment that is increasingly formal, but always physically practicable. So about maybe 2/3 of the way through the talk, I'll change gears and I'll describe a top-down point of view, so that this point of view is more body-centric, and this point of view is going to be more world-centric, where we abstract the robot in the environment to be, the robot is a point, let's say a point particle in the environment, and we want global planning, and we don't want to have to know that much about the environments in advance. I'll use navigation functions as the primary vehicle for representing tasks. There's going to be an environment abstraction through change of coordinates, as I hinted before. And then I'll describe some of our imperfect integrations of these reactive motion planners into more AI-style deliberative architectures. And that will lead me to the last bit of the talk, wherein I I complain about not having enough people to work with me on this category theoretic agenda. We've made very, very exciting first strides through work of Paul Gustafsson and Jared Culbertson, mathematician collaborators of mine. But we need more help. We'd like to develop a real type theory that's a little bit more practicable and might make it possible to have this integrating step be formal, at which point we'd actually have a formal programming environment for real world robot tasks. Okay, so that's the agenda. And let me start with the bottom up point of view on which I'll spend most of my time. I'm trundling along unless I get I can't see anything because I only see my PowerPoint on the screen at this point. So, feel free to interrupt if you want, or let David intermediate if he would like to. Yeah. Okay. So we were really, really inspired in the 90s. Martin Buehler, one of my first doctoral students, went to become the first chief robot scientist at Boston Dynamics. And Mark Raybert, was the CEO of Boston Dynamics, pioneered an amazing series of robots that use this kind of bouncing gait as the heartbeat. We took that bouncing gait and we invested it in a number of different morphologies. So here is a 4 degree of freedom sagittal plane machine. The mass center of this machine is represented by the white ghost pogo stick. And what I'm trying to represent here is that the discrete dynamics of the pogo stick, if you take the Poincare section, are almost indistinguishable from the Poincare dynamics of this juggling machine of Martin Buehler's. And I want to make the point that you can embed the same slip spring-loaded inverted pendulum, this white pogo stick, can be embedded in the red physical hopper in many, many, many different postures. And so it depends. You get to choose what the invariant attracting submanifold is that you want to hop along, whether you want to be more kangaroo-like or you want to be more upright and human-like. Okay, so these ideas were practicable in the sense that Martin invented the first legged machine ever to run, the first legged machine ever to run at all outside and without any plug in the wall. And Rex, if you run this Rex robot over a scale, a force plate, the force plate will feel like it's a spring-loaded inverted. It'll feel like there's a pogo stick running over it. All right, and so that's an example of this template anchor hierarchical relationship where the high degree of freedom body is anchoring a very low degree of freedom, in this case, 2 degree of freedom sagittal plane pogo stick. And that's what I'm trying to get across with this little emblematic basin that's got a furrowed valley within it of much lower dimension. So here's the invariant submanifold. There's an attraction down to the invariant submanifold, and then on the invariant submanifold, you're getting down to the boss's call. So I hope this cartoon is making a little bit of intuitive sense. Fast forward 15 years, I had a wonderful series of students. We kept working away at this Raybert vertical hopper. So here's the thesis work of Avik Day. Avik Day is the co-founder and now the chief science officer of a commercial outfit called Ghost Robotics that's selling versions of this machine. Avik pointed out that you could do a parallel composition of 2 vertical hoppers, wherein if the mass distribution was right, they wouldn't, the vertical, so if you take a sagittal plane view of this, sagittal plane is the plane that runs through the body, the symmetric axis, the symmetric plane of a bilaterally symmetric animal, like all the tetrapods are in the world. So take the sagittal plane view of this thing, the side view of this thing, and you can see that it's got back legs and front legs. And Avik's controller is running a Raybert, not a Raybert vertical hopper, a modification of a Raybert vertical hopper independently on the back legs and independently on the front legs. And when the mass distribution is favorable, you'll get a limit cycle, a hybrid limit cycle into 180 degree out of phase bounding. If the mass distribution is wrong, you'll get what the biologists call pronking. Now, you'll settle down to where both hoppers are in phase rather than out of phase. You can disrupt that with more information in between them. But we're interested in these highly decoupled, highly decentralized feedback reactive strategies because they're so very, very robust. You can interfere with this this is the slot hopper template, as Avik called it. You can interfere by kicking it with a fore-aft perturbation. This is another parallel composition, and you can thereby get fore-aft motion of bounding, and you won't destabilize it even with very, very, very severe perturbations, as I tried to show you in the movie. So here's an example of a parallel composition. Parallel meaning this basin and this basin didn't know anything, or they didn't know very much about each other, and they just coexist, and together they form a limit cycle that has the right phasing relationship when the mass distribution is favorable, or when you disrupt it in the appropriate way. Okay, and so this parallel composition was in the service of anchoring in this 3 degree of freedom rigid body the 1 degree of freedom, something akin to a 1 degree of freedom hopper. We've also gotten, okay, so this is an example of a parallel composition being used for a hierarchical purpose. Here's work much later by Turner Topping, who took this miniature and he sequenced a variety of these behaviors to enable the robot to jump up, reach the door handle, open the door handle, and then, walk through the door, which otherwise it would never be able to open because the door handle is too high. And he developed a family of these sequences. What we weren't able to do in Turner's work until very recently is have these sequences actually be formal. And here's an example of a sequential composition, which is an idea that goes back to the days of Al Rizzi. Al Rizzi was a former doctoral student of mine. He got pried loose from his faculty position at Carnegie Mellon. He's now the chief robot scientist at Boston Dynamics. Those of you know about Boston Dynamics. The idea that Al had with Rob Burridge when he was then a postdoc in my lab was to try to sequence basins together by allowing controller phi 2 to turn on if and only if the state from phi 3 entered its basin. And of course, if you make sure that the attracting set of phi 3 is included in the basin of phi 2, then you're guaranteed that that's eventually going to happen. So Turner was able to make his hybrid system now behave in this sequentially composed way. All right, and so the next, I guess, 10 minutes, maybe 15 minutes of the talk is going to be all about how to do a better job of formalizing these practicable sequential, parallel, and hierarchical compositions of these basins. Okay, before I do that, I need to talk about abstracting the environment. This is now work that goes back to Aaron Johnson. Aaron is now a professor at Carnegie Mellon in robotics and mechanical engineering robotics. Al was very interested in getting the Rex robot to jump onto things, to be more athletic than it had been. The Rex robot was really good at running over rugged terrain, but it wasn't that good at surmounting energy barriers, right? So there's a potential energy at this level, and you'd like to get the mass center of the machine up to this energy level. And so you have to use your battery, you have to inject energy, kinetic energy into the body. And then, of course, you have to steer that kinetic energy capably in order to get the ascent of the energy barrier that you wish. So Aaron came to realize that what really mattered to the robot in this environment was he could take a very, very, very crude piecewise linear representation of the sagittal plane view of this environment. In fact, let's just think about the ground plane that the robot starts on, and let's think about the various Lagrangian systems that are defined by the various constraints. Let's assume that the robot has a nose that can slide, and it's got a butt that can slide on the substrate, and it's got a leg that can stick, and it's got a leg in back, and it's got a leg in front that can stick. Let's never mind for now the middle leg, because the dimension will get too large for me to display in this cartoon. But Aaron was then interested in abstracting the interaction of these very constraints, realizing that abstractly you get a simplicio complex, right? So that no legs down, if you think about the position of the Boolean variable corresponding to the butt the leg, the front leg or the nose, right? Then here, no port of the robot touches the ground. In these configurations, either the rear leg or the front leg is touching the ground and sticking. In these configurations, either the butt or the nose is touching the ground and sliding. In this configuration, you're getting both legs, so you only have 1 degree of freedom left. Here are 2 other 1 degree of freedom configurations where the nose is sliding and the leg is now forming a closed kinematic chain. It's a linkage, if you will. All right, and on and on and on. So I think you can see that abstractly, the ground and the affordance of the ground to the kind of ground reaction forces that you can use the legs and the nose and the butt to build up in the mass center all have to do with where you are on this simplex. And so what Aaron was able to do was able to feed forward controls, taking advantage of one or another presumed flight up this Hasse diagram that elaborates the energy barrier, the ground reaction complex to surmount the energy barrier. And here's a particular instance where first he's loading kinetic energy into the springs, then the springs add kinetic energy to bring the robot up to the roof. And that's a sequence up this Hasse diagram. I'm running out of time already, so I'm gonna fast forward to, this was all open loop, okay? What we'd much rather do is we'd rather plan in abstracted agent coordinates on the same, or an abstracted version of this ground reaction template. Let me see if I can motivate this a little bit. Here's the box jump that I showed you. This is a true sequential composition. And this sequential composition involves a sequence of pogo stick maneuvers that all think that they're single-legged and interacting with one or another plane of the ground reaction complex, now reduced to a sagittal plane piecewise linear representation. So ordinarily, when roboticists are planning complicated behaviors, much more complicated than this one, but this one is complicated enough, they're thinking about the entire mode sequence. What do I mean by a mode sequence? Well, you've got, if you're taking a sagittal plane view, then you've got 2 legs, you've got the rear pair and you've got the front pair, okay? And then you've got 4 modes or 4 different environments. Why? Because one environment is this piece, that's piece 1. Another environment is this piece, let's call that piece 3. Another environment is this piece, let's call that surface piece 2. And then, of course, there's the environment with no contact. And your interaction, your legged interaction, of course, all of these pieces are decorated by geometric variables, and they're also decorated, importantly, by their mechanics properties, importantly, whether they're sticking or slipping. If you take the point of view that you need to know what the mode sequence is up this Hasse diagram, then you're going to have to have a different controller for a super exponentially growing number of these mode sequences. That's not a happy situation. So what you'd rather do is you'd rather plan, yes, okay, at this point, we were still planning routes up the Hasse diagram of the ground reaction complex, but we were trying to do it with just standardized anchorings of the same template up each edge, okay? So again, I'm already running out of time, so I won't do this the justice that I had thought to. I'm trying to show you that these are all closed loop. These are sequential compositions. Each anchoring is guaranteed to get to the guard that leads to the transition that you wanted to get from this mode where both 2 legs are on the ground to this mode where 1 leg is on the ground and the other leg is rearing up, to this mode where you're in the aerial phase, to this mode where, and I'm trying to paint them out in this sequence of still shots, okay? And so this, unlike the earlier sequencing work that Turner was doing, or the completely open loop work that Aaron Johnson was doing 10 years ago. These are very, very strongly repeatable as long as you line the sagittal planes up very, very nicely, okay? And that's a big if that I'll address in the next slide. Okay, the problem here is that we're still spending too much time. We're still, if we've got to tune every possible anchor, there are m possible modes, and there are 2n to the k possible substrates, then we're still doing a lot of control work. We'd like to have something much more modular than that. Well, the last work that Avik Dey did with me before he turned himself from a great academic into a corporate titan was to come up with a universal embedding of pogo sticks into sagittal plane machines, okay? And I won't go into the details of how this parallel composition works, but it really is a parallel composition. It uses a hybrid version of dynamical averaging. If any dynamicists in the room, you know, averaging has been around for decades. It was really perfected for classical systems by the Soviet mathematicians in the mid-20th century. So Avik generalized this to a subclass of hybrid dynamical systems, and he achieved thereby the ability to mix and match pretty arbitrary body and distinguishing between the posture of the orientation of the body in SE2. SE2 is the configurations of a rigid body in the sagittal plane, okay? And so it's got translational degrees of freedom, and we're going to think about those translational degrees of freedom as either vertical hopper templates or pogo stick templates, spring-loaded inverted pendulum templates, or possibly if you want to do, if you need to be doing swinging from the vines, or if the ground is too slippery and you can find a handhold, you might want to swing from time to time. Okay, so these are the translational degrees of freedom of the sagittal plane. And in parallel, we'll think about two different posture families, one posture family involving a steady held pitch of the orientation, and another posture family involving a steady velocity, non-zero velocity, but a velocity regulated pitching body. And that gives us now a whole palette of parallel compositions that we can use to spell out words of syllables, where I'm interpreting now the letters as being the basins in the pitch degree of freedom, or the basins in the translational degree of freedom corresponding to these cartoons. The syllables are the compositions. And what we're thinking about is we're planning in the templates, we're planning in the vowel letters, but we're executing in the postures, meaning we have to think about obstacles and barriers in the body space, right? Because that's the thing that's going to be bumping into the substrate if we're not careful, okay? And for example, here's the syllable VI, and it's adjusted so that we can get about a 270 degree flip, right? It's a constant pitch with a pogo stick hopper. Here's the same VI with a higher pitching speed relative to the apex height, and that gives you a 360 degree flip if you want it. In contrast, here's the syllable SA, which is the steady held posture. It's not steady yet, but you'll see as soon as this thing leaps off the bar, we're in the A translational degree of freedom template. And we're trying to get a steady posture because we want to stay vertical so that we can grab this next bar, okay? And so this is the syllable SA. It's the steady posture leap of the pogo stick robot. And here, I think Turner's going to repeat this again. You can see it in slow motion that he's swinging up not in steady, he's swinging up just in the A. And when he swings up again, he's now going to swing up in the configuration that holds the pitch steady and enables him to land without losing too much vertical height. Alternatively, it could have been that you faced monkey bars with long distances between the bars. And so you can't possibly manage to catch the next bar unless you use the VA composition, where you're allowing your body to kinematically extend your reach. All right, and so these are now syllables of basin letters, and these syllables of basin letters in turn will be strung together to begin to form words, if you will, compositional words. And again, these things are all formally composed. They're sequentially composed in this formal sequential composition. I'll say a little bit more about it later. And so we're beginning to have words of energy ascent that plan in the template and execute automatically in some composed version of that template with whichever posture you felt was going to be necessary or useful to get up the grand reaction complex that represents the barrier that you're trying to ascend. Okay. I'm going slow here. Sorry. I guess there's one last idea I want to get across, and then I'll move on to the top-down view. Okay. So far, the weakness in what we've been doing, I think it's clear, is that we have this grammar. And this grammar, it's not really a grammar, it's really like morphophonemics, okay? We have this compositional way of forming letters into syllables and syllables into words. Here's the feedback version of Turner Topping's door handling thing. And we're doing the so, and I think you could see at that point there was the active vertical hopper, and then finally we did the steady vertical hop to get to the door handle. To give you some sense of the virtues of this kind of reuse and modularity, you can do very different behaviors with almost the same syllable sequence. This is almost the same word, it's just the final syllable is a little bit different. All right, so we're really happy, increasingly happy with the words that we're able to spell out in the sagittal plane. But if you misalign these robots in yaw, then these tasks will fail miserably, because the presumption here was that the sagittal plane of the environment lined up with the sagittal plane of the robot. So the last piece of body level grammar, if you will, that I'll leave you with is the more recent work that's been done by a present doctoral student, Tim Greco. Tim has been working on anchoring the spatial body, SE3 body, in anchoring the SE2 sagittal plane into the SE3 formal rigid body of the robot. I'm going to give you a peek under the hood of how to build these Lord Kelvin-like energy basins. And Lord Kelvin's insight was that the potential function landscape is inherited by the kinetic energy landscape. If you read his 1868 treatise when he was still Sir Peter Tate, all motion is going to end up at the extrema of the potential function. You would like to encode the desired states at the minima. Unfortunately, the desired states may incur undesired states as well in the following sense. If you're going to have a smooth potential and you want non-degeneracy, and for example, you want point extrema, then topology is going to, of course, force more than one extrema. If you want set extrema, so that instead of a Morse function, you want a Morse spot function. Why do we want Morse spot? Because we don't want we want arbitrary pitches to be stabilized. We don't want to constrain the pitches at all. We want to constrain SO3 down into the pitching of SE2 at its equator. Okay, if you think about the hop vibration of SO3. And of course, you want the mass center of the robot to be at the inertial center of the sagittal plane of the environment. Okay. If you're going to do this on the rotation group, namely, what do I mean by this? Namely, if you want a non-empty minimum set, that is, you want a low point where the body frame is exactly aligned vertically over the sagittal world frame, okay? And the orientation of the body frame is, we don't care what the pitch is of the body relative to the sagittal plane or world, but we care very much that the yaw and the roll are aligned with the body. If you want that plane to be an attracting invariant submanifold, and you want it to be smooth so that you have a field, a gradient field, which is attracting down to that invariant submanifold, you're going to be stuck, of course, with another image of that plane, the antipodal version of that plane, where the robot is twisted up, okay? And you're stuck with that for topological reasons. If you want this to be a smooth controller, of course, there's only a set of measure zero that's going to go to these high, bad, twisted configurations. Even if you're a badly bucking Bronco, you're not going to get there in the physical world. So you're stuck with it, and we'll live with it. I'll remind you that Avik had a parallel composition in the sagittal plane that gave him this abounding sagittal plane behavior. Tim is now going to add in his Morse bot function, and now we can perturb away from the SE2 sagittal plane. Even pretty dramatic disturbances are reacted to pretty nicely by this boundingly energetic machine. Maybe I should try to play that one more time. I don't know if are the movies playing well enough for you to see what's going on in this thing? It's slow-mo?
Yeah, they're playing pretty well.
So these are pretty dramatic disturbances at many factors of velocity perturbation of the regular steady state. So this Morse spot function is working quite nicely. And because it's a parallel composition, we can take this thing, and this box jump in the sagittal plane now gets lifted into the spatial machine. It's exactly the same code that Tim is using. Tim took Turner's code from the sagittal plane Minotaur into, this is the Ghost Robotics spatial machine that's got abduction degrees of freedom as well in its hip, rather than just 2 degrees of actuated freedom. It's got 3 degrees of actuated freedom. And so it's exactly the same code, parallel composed with this Morse spot function in the sagittal plane. The great virtue now is that if you have a yawing misalignment or some other disturbance, this would have destroyed the sagittal plane version of the grammar, but with this extra anchoring degree of freedom into the sagittal plane, you're getting pretty reliable hops in free space as well. Okay, I'm going to skip. I'm going to skip this slide. I'm going to skip. I will show you this movie to give you a sense of another virtue of this grammatical point of view. Is if you were wrong and you stepped on a banana peel, you'll be catastrophic unless you can recover and realize that the word that you thought you were spelling is the wrong word for this environment, and change your mind in real time about the word that you want. And even if you continue to slip, there's a notion of a virtual substrate that could enable you to replan your way up this template level ground reaction complex graph and be reactive in real time. If there's time at the end and there's interest, I can come back and talk about what's going on in this slide. All right, I want to change gears. I want to stop talking about the bottom up. We're very, very excited. I intentionally spent a lot of my time on the bottom up point of view because that's the point of view that's the messiest it's the messiest to formalize. And we think that we're at the point of having morphophonemic rules that begin to give words. And we should now try to figure out what clauses of command could be formed from those words in a formal manner. All right. So that brings me to a top-down point of view where I'd like to now take, instead of thinking about the body-centric view of the robot, I'd like to think about the world-centric view of the robot, let's say as a point. And I'm going to go back to work done by my doctoral student, Yalon Rimon, 30 years ago. He's now a professor at Technion. And what he's showing you here is that if you have a complicated maze and the boss wants you to move around in this maze, that maze is deformable down to a topologically equivalent model space that is geometrically very simple. And what Ilan did in his thesis is he built up, this is a publication, and it's the only publication I have in the Transactions of the American Mathematical Society. We formally built diffeomorphisms for arbitrary forests of trees of stars down to their topological models in sphere worlds on the plane. And this gives you completely guaranteed locomotion, completely guaranteed gradient descent or Lagrangian descent, because you remember that these gradient potential functions also embed in Lagrangian systems, according to Lord Kelvin. So you get, of course, there are going to be spurious saddles, but there won't be spurious mins. So you're guaranteed to get to the boss's destination, which is low. You're guaranteed to avoid the obstacles which are high in the potential sense. There's saddles in the Lord Kelvin kinetic energy sense. Saddles, of course, are not repelling, but there's no physically observable set of initial conditions which will get you there. Okay, so this is a good theory, a motion plane. This is a reactive global motion planner and executor, albeit it requires perfect prior information about the environment in advance so that you know how to deform the footprint of the labyrinth down to its topological model. Fast forward 30 years, and Ömer Arslan, a doctoral student who just recently graduated, he's now a professor at TU Delft, introduced a related but simpler point of view that built an instantaneous Voronoi diagram of the robot amidst simple obstacles and servoed the robot toward the local free workspace point, which is metrically closest to the global destination. As soon as the robot starts servoing toward that metric projected point on the Voronoi boundary, of course, the Voronoi cell will change. And the interaction between the change of the Voronoi cell and the change of the robot's configuration gives you these guaranteed to avoid obstacle trajectories down to the destination. You don't have to know anything about the environment at all beforehand, except that it's geometrically trivial, that it's a topological model. Fast forward again a few years, and my one of my most recently graduated doctoral students, Vasilis Vasilopoulos, merged Ilan's ideas from the 90s with Ömer's ideas from the early teens. And I'm just showing you a real-time version of one of these deformations of a metric, of a complicated puncture into its topological model. What Vasilis did was he worked with our colleagues, Kostas Danielidis and his students in AI and computer vision at Penn. We used their deep neural network recognizer to recognize families of chairs and desks, and we made the assumption that's pretty good in the physical realization. We made the assumption that after you train up these perceptual networks, as soon as the robot sees any square, it'll instantiate that square as the detailed footprint that square has. It instantiates those footprints and builds up in its semantic space a footprint of the topological obstacle formed by, the configuration space of the disk in this world is different from the metric properties. You have to shrink down the robot to a point, and you have to dilate the obstacles by the radius of the robot in order to get the footprint in the configuration space. This is the footprint in the configuration space, and under these assumptions, the footprint in the configuration space has a known topological model. Vasilis is now deforming this known topological model into the model space and now invoking the Ömer Arslan control in the model space, pulling that back into the metric version, of course, each time you have a different sensory input, you've actually not got a classical system any longer. You've got a hybrid system, because each time the perceptual world changes, each time you get a different subset of the obstacles into your sensor footprint. In this orange circle is the sensor footprint of the robot. You get a completely different topology. So you need to instantiate a completely different model space. That's okay. You need to make sure that the Lyapunov functions from the prior model space are not being raised by the Lyapunov functions in the next model space. That's this notion of sequential composition. And if you get that right, then you can prove global convergence for partially known environments. That is, you grew up being trained on what chairs are and what tables are and what bicycles you'll encounter in the room. And you're using a hybrid version of these instantiated, deformed, metrically deformed versions of the topological models in this hybrid sequential composition manner. I'm not going to bore you with the details of the architecture, but this works quite well in the physical world. And the formal properties are based upon the assumptions we make about what the deep neural network is doing. Of course, no one can prove anything about what neural networks are doing. We're just making assumptions about what they do. So modulo those assumptions, we get formal guarantees. The point I'm making here with the boring garbage can robot is that the high-level guy can't tell the difference between a complicated bucking bronco, like a legged machine, and the simple garbage can robot that's got a differential drive in it. These algorithms assume that the sagittal plane of the machine is commandable in continuous time, and it's the job then of the body-centric part of the robot architecture to follow that sagittal plane view. And that brings me to, I'm now really running out of time. I'm going to finish in 3 minutes. That brings me to, I'm going to skip this. That brings me to the last part of the talk that might be interesting to more of you in the on the call, which is where we're trying to get formal the relationship between the deliberative layers that are doing the motion planning and the gate layers, or the body-centric layers that have these formal morphophonemic spelling words. Okay, so here's work that Vasilis did with my colleague George Pappas at Penn, who's an expert in applying linear temporal logic as a specification language for classes of Buki automata. We're trying to buy out of the whole Buki automata and substitute a formal linear logic in place of this architecture that I showed you before, and have the linear logic then call out the template level sagittal plane commands that will then be refined into these body-centric ground reaction force algorithms. The punchline, and finally I'm getting to category theory here. Jared Culbertson, who's a mathematician at the Air Force Research Lab, together with Paul Gustafson, who's now a postdoc in my lab, developed a formal category theoretic model of a pretty physically valid model of hybrid dynamical systems, wherein this double category takes advantage of the fact that we're always going to have Conley basins. We're going to be using the vertical morphisms. The vertical morphisms are going to represent semi-conjugacy. So in particular, they represent the change of coordinates from the metrically naive but topologically valid model into the metrically informed topologically equivalent space, or possibly template anchor compositions where we're embedding a low degree of freedom thing as an invariant attracting submanifold, okay, in the higher degree of freedom body, maybe eventually. The notion of sequential composition, Paul and Jared were able to encode through this notion of a directed system, and that's the horizontal composition. That's, I think, a little bit more straightforward. Paul came up with a really nice way of representing through a pullback of subdivisions the kind of hybrid version of a limit cycle that you need to get these these limit cycle attractors to work in their category. So that was nice. What's not nice about the category is that it's very naive about parallel composition. It assumes that there's no crosstalk at all. Paul has been developing a type theory to represent the naive top-level, top-down ideas that I described in that one slide. We're not close to having a view of how to extend. The parallel compositions are still too naive to be useful at the body-centric or bottom-up level that I discussed. But I'm extremely excited about the prospects for having now a formal type theory that would enable a programming language such that LTL clauses could be translated in correct by design linear logic clauses that automatically compile down into these sagittal plane maneuvers. Let me stop. There's a bibliography, there's a list of references at the end of the abstract if you're interested. I understand there's going to be a recording of the video. So, those of you who are really interested, here's the more extensive bibliography list. I'm going to stop, and I'm sorry I wanted to leave 15 minutes. Instead, I left hopefully 9 minutes for discussion. David, what do you think?
Okay, great. Thanks, Dan.
Maybe what I'll do is I'll turn off my share so I can see people. Is that okay? Sure. Unless people want to see, I don't think, if you want to see slides, of course, I can bring the slides. There's Brendan. Hey, Brendan. Good to see you. Yeah, I don't know how much of that I got across, but I'd love comments would be, or questions would be strongly encouraged.
Okay, great. So I just had a question, very naive question. In the Hasse diagram, are the arrows representing I can get from A to B? Is that what that means?
They're representing, it's a pruned version of the Hasse diagram because there are parts of the Hasse diagram that don't mean very much physically, that have, the robot levitating in useless ways. So you have to prune it. It's not the logical Hasse diagram, it's a pruned version. And we're going to prune it more to allow only edges for which we have a template edge. So we need a guard reset across the edge composition before we allow that edge of the Hasse diagram to persist in this ground reaction complex representation. Yeah.
Okay, great. Thanks. And it looks like we have a question from Topos Institute.
Hi. Thanks for the talk, Daniel.
Hi, Evan.
Hi. I'm Matteo. Evan is there, but anyway.
Oh, sorry. Okay, sorry.
It's everybody in the office.
Yeah, I'm just reading. I'm reading your name. Yeah. Okay. Go ahead.
Sure. So I think in the last slide there was a small theorem that caught my eye about this double category hybrid systems.
Yeah.
The reference for that?
Yeah, that's in the Transactions on Applied Category Theory. It's not a journal I've ever published in before, but this is courtesy of Jared and Paul. And that reference is in the abstract if you wanted, and if you go to the movie, if you can't, or if you send me an email, I can send it to you. But it's in the abstract. It's cited in the abstract.
Just to check, if it's TAC, that probably stands for Theory and Applications of Category.
Right.
Thank you, David. Yes. TAC for us means Transactions on Control Theory. So I'm sorry. I don't habitually publish in Transactions on the American Mathematical Society, and I don't habitually publish in Theory and Applications of Categories. But if you guys come play with us, then we'll publish more together in such journals, right?
Sounds great. All right, I will look it up then. Thank you.
I would never be able to prove such theorems. I was hanging on by the subway straps, right? They were doing all the work, and I was telling them, no, that might be good mathematically, but it's kind of stupid engineering wise, right? That was my contribution to this.
So if I could just ask a question about that again. So the parallel composition is saying that they don't need to send each other signals because all the signals will run through the body itself. Is that the idea?
Yes, the sagittal plane composition is pretty accurate in that that because of this nice more spot function, you're pretty decoupled. The only coupling in the Lagrangian system is in Coriolis forces, and those Coriolis forces are pretty negligible unless you're really, really, really badly perturbed, in which case you're going to want not to collapse and move out of the basin rather than try to get down to the attractor, which is what you saw in that movie. So the sagittal plane more spot function is an example of something which is pretty legitimately naive, whereas and the fore-aft thing of the slot hopper that I was telling you about, that's legitimately decoupled if the mass distribution favors the coordination that you want. If you want it to be bounding, then the mass distribution better be away from the center of the body, like a seesaw. And if you want it to be pronking with all the legs in phase, then the mass distribution. And if you don't want, if you have the wrong mass distribution for the gate that you want, then you have to put a little bit of disruption in, and it's no longer quite as parallel.
Okay, but so what you want formally is to be able to say, like, you want to have kind of normal conditions and abnormal conditions, and be able to say, under normal conditions, we can ignore this, and under abnormal conditions, this is going to become an issue. Is that
really what we'd like? Paul is working hard right now on a notion of epsilon T chain conjugacy. We're using hybrid averaging to get the crosstalk to be ignored in the average. So if those of you who are familiar with Arnold's or the Soviet mathematicians' work on classical averaging know that what you get is you get epsilon close to a decoupled, to a system that has the invariant submanifold that you want. And the trouble is that the Conley theory, which one of his great ideas was to use Conley's epsilon T chains to get the hybrid thing to work. Unfortunately, the topology doesn't know anything about invariant submanifolds. It only knows about attracting sets in the sense of Conley. And so what Paul's trying to do is see if he can get an epsilon T chain view of attracting invariant submanifolds. And he's a smart guy, but any of you who would like to work with us, we'd welcome that. Yeah.
Cool. Looks like we have a question from Valeria. Maybe it'll be our last one, but you're muted, Valeria.
Hello, Dan. Thanks very much for a very interesting and hard talk for me to follow. But since you mentioned
thanks for coming.
It's just different sorts of backgrounds, right? But since you mentioned linear logic and linear temporal logic, I wonder if you could give me a bit more of intuition about why linear logic and why.
Okay, our category almost surely can't have exponential objects in it because I don't know how to deal with infinite dimensional spaces. Okay, so I'm stuck without at least it's not going to be a Cartesian closed category. The category is complete and co-complete, and it pullbacks. It doesn't have exponential objects, and so. The wisdom that I don't know this, but this has been beaten into my head that if you're not going to have a Cartesian closed category, you're not going to have you're not going to have simply type lambda. That's not going to be your type theory. And so you're not going to have as good a language as you might like. But, I understand that the computer scientists are familiar with the emergence of linear logic from settings where you can't duplicate things. And in the world of robotics, of course, you shouldn't have expected to be able to duplicate. It's not, we're doing physical work with physical masses. We're not doing information transfer with electrons and electrical signals. And so it shouldn't come as a surprise to me and us that we're not going to get, we might embed this thing in some kind of a Cartesian closed category, which is what the LTL, as you may know, these modal logics have good properties. They're very, very expressive, and people have looked, there are some category theoretic treatments and type theoretic treatments of them. The LTL people in control tend not to take that point of view because they have they don't ground in the physical world the way the Buchi automata can be forced to ground. So we want to do an end run around these Buchi automata. We want to stay on the church side of the church-Turing divide, right? Because our physical machines are not DFAs. The Lagrangian, our automata are not discrete finite automata. They're Lagrangian automata. They're analog computers.
Okay, that's very exciting. Thank you so much.
Yeah, come
But
play
one
with
more
us. Yeah,
thing
yeah,
on
yeah.
that one.
That's right. We want to get
Do
you
you have
excited. Yeah.
Do you have a linear exponential object then? Because
Say it again.
do you have a linear exponential object?
I don't think so, but even though people have explained to me what that means, I still don't understand what that means well enough to be sure.
Fantastic. Okay.
I'm desperately trying to learn. Brendan was here and forced me to start talking with him about category theory, and that was 10 years ago. And so I'm beginning to understand how to read some of these books, but I'm a slow learner.
No, thanks a lot. That's very good. Thank you.
Well, I think we should stop the formal presentation here and thank Dan again.
My great pleasure. I really appreciate the invitation, David. Thank you very much. And I mean, you can see there's plenty of work for lots of different people to do if we could get you interested in this. There's much more work than my small group can do. Maybe we'll